Here we have the series, infinite series of 1 divided by 5 plus the square root of n to the third. We want to use the direct comparison test or the basic comparison test to show that this infinite series right here converges. And so if we want to use the direct comparison test, we'll call this sequence right here A sub n. And then we need to come up with a B sub n that is similar to the A sub n, and then show that the series B sub n converges, and then that will show that A sub n converges also. So we want to let A sub n be this sequence right here. And then for B sub n, we just drop the constant phi. And this also can be rewritten. This is the n to the third of the second root. And so this can be rewritten with rational exponent of 3 halves. So we have 5 plus the square root of n to the third. This is greater than the square root of n to the third. And if we take the reciprocal of the left side and the right side, then we have to reverse the inequality sign. So 1 divided by 5 plus square root of n to the third is less than 1 divided by the square root of n to the third. So if we have 5 plus the square root of n to the third, which is greater than the square root of n to the third, and then we take the reciprocal of both sides, then we have to reverse the inequality. And so this is less than that, so that means that the series, this is the series A sub n this is less than the series B sub n. And so now that we got this part, we have shown that the summation of A sub n is less than summation of B sub n. And now we need to show that B sub n converges before we can say that the series A sub n converges. And so now let's look at the series B sub n. And notice that this is a P series with P equal to 3 halves. And recall that if we have a P series with P greater than 1, then the series converges. And so this right here, we have shown that the series of A sub n is less than the series of B sub n. And we also shown that the series B sub n converges to some real number. And then now we can say that by direct comparison test, this series right here also converges. And the reason behind this is because we've shown that this is converges, and therefore this must equal to some real number s. And this series right here is all positive terms. And so this series is bounded between 0 and s. And then also it's bounded, and that's why it converges. And again, once more, if we want to show this series right here converges, then we call this A sub n. And then we need to come up with the sequence B sub n that is similar. So in this case, we let B sub n be the sequence without this 5 right here. And that will lead to 1 divided by 5 plus the square root of n to the third is less than 1 divided by the square root of n to the third. And then next, we shown that the series 1 divided by the square root of n to the third, which is the same as 1 divided by n to the 3 halves. And this is a p series with p equal to 3 halves, and this is greater than 1. And we know that if we have a p series with p greater than 1, then the series converges. And so we have shown two things. A sub n is less than the series B sub n, and we have shown that B sub n converges. So we have shown these two things right here. Therefore, we can say that the series A sub n converges also.